The third main feature of ionic compound nomenclature involves something called polyatomic ions. Polyatomic ions. We've addressed this briefly before, but let's go ahead and get into a little bit more of what they are. It's an ion, right, as it is called a polyatomic ion. So it's an ion, so it's a charged particle, but this time it's actually part of actually made of several atoms bonded together. And that's why it's called a polyatomic ion. It's an ion formed from a group of bonded atoms treated as a single unified group. Now, let's make sure we draw a quick comparison here. The other kind of ion, at least in this regard, has been monatomic, right? So let's compare that to monatomic ions. So these monatomic ions would be like having a single ion. That's represented by a single atom. But polyatomic ions, these are an ion, or these are ions where you have multiple atoms bonded together, kind of like this right here. So the nitrate ion, this is the one that we're looking at right there. The nitrate ion, again, this is just a new thing that we're introducing, is an ion where you see 1, 2, 3, 4 atoms all together bonded. This is a Lewis structure you might recognize, but it overall has that -1 charge. And so this is considered a polyatomic ion. We're not concerned about the charge on this or the charge on that and on that and on that individually, right? We're saying this whole thing together has a -1 charge, and what these individual parts actually are charged, that's irrelevant. That's not part of the discussion. And again, comparing that to the nitride ion, notice how you have a different ending here, but the nitride ion, this is what we're familiar with already, this is going to be N with a -3, so it's a single ion that has a -3 charge overall. It's not N with a bunch of other stuff attached to it, it's just N, that's it, and it has a -3 charge. Now, you may have noticed that the ending is a little bit different, so let's go and break that one down some. Most polyatomic ions use some element root, right? So whatever element you may be familiar with already, and then has either an ite or an ate ending. So ite, ate. Ate as a prefix, or excuse me, ate as a suffix or as an ending. Ate means more oxygen compared to ite, which means less oxygen. So if you ever see ate and ite together in a single polyatomic ion or discussing polyatomic ions, you know the H is simply going to have a little bit more like oxygen than ite. All right. Please do note, again, we're specifically talking about the element oxygens that are added to a root element. There's also going to be some potential confusion with that "ide" ending. So the IDE ending is what we've been using a lot before this, but now we're kind of introducing in something else that's not going to have that "ide" ending every time. And I'm counting on you to identify that and make that distinguishing characteristic known. And anytime you see the "ide," or at least most of the time you see an "ide," that refers to a single monatomic ion. Right? There are a couple of exceptions, of course, but for the most part, anytime you see an "ide" ending, we're typically looking for a single element, and how that ion is just going to be a single atom. It's not going to involve a group of them, especially no oxygens. So looking at these right here, I've given you a couple of example ions here, and I'm asking you to identify which ones are going to probably refer to a polyatomic ion. Well, let's try this out. Right, this first one's chloride. You recognize chlor as the element, probably referring to chlorine. And then you have the IDE ending, which means that this is going to be a monatomic ion. So the question is asking you to circle or identify which one's a polyatomic ion. That's not going to be it. Chlorite, in this case, chlor, CHLOR. That's, again, another prefix that refers to the root anyway, that refers to the element chlorine. But then it has an ite ending. So ITE, that's characteristic polyatomic ion. That's going to be a polyatomic ion for sure. Nitrate, phosphide, sulfite. Go ahead and try these out to see that you can follow the pattern. So how do you identify polyatomic ions? And this again is going to take a little bit of sort of guessing, and I get that we haven't really addressed them a whole lot yet. But for this slide, I want you to take a look at these 6 compounds that are provided, and in each one, I want you to try circling what's considered the cation, and then the anion, put a square around it. So if it happens to be a polyatomic ion, anion, we're going to add a little star next to it. So let's try a couple of these out. First of all, number 1, NaNO3. Okay, well, this is, again, kind of new to us because we have only seen binary ionic compounds where you have 2 elements. This one has 3 different elements. You have the Na, you have the N, and then the O. So let's try this out. First of all, we need to figure out what our cation and our anions are. Well, as sodium, right, Na, you recognize that. That's a metal, right? So I'm going to kind of separate these where this is going to be the metal and this is going to be the non-metals, right? And that's the start when we usually identify these ionic compounds. That's one of the first things you have to do, is recognize that this is going to be the metal sodium, and the rest of these Na and O, those are going to be your nonmetals. So you can probably see a pretty clear divide here that the left side of this metal, that'll be your cation. So I'm going to go ahead and circle that. I'll use blue now. I'll go and circle Na as the cation. Then everything else, well, that's NO3, and even though we don't necessarily have a whole lot of familiarity with it yet, this is going to be your anion because those are your nonmetals. So we always associate nonmetals as anions. So I'm going to go ahead and refer to that and circle all of that as my anion. And of course, if the anion is a polyatomic ion at a start, well, again, how do we know if it's a polyatomic ion? Well, this is, again, a single anion. It's got multiple atoms. In fact, it has 4, right? 1 nitrogen, 3 oxygens, has 4 atoms. So that's a polyatomic ion. So I'm adding a little star next to that. Let's try the second one. So it's the second one here again, same process, right? This is a compound. You've got Fe, iron, that's a metal. You've got C2H3O2. Right? It's obviously a lot of elements, but again, what do you notice about all of them? It's a nonmetal, this is a nonmetal, this is a nonmetal. So all 3 of those are your nonmetals. And the way this works is that, again, if we're going to try and identify what's in it, we're going to circle the cation, which I'll do in blue here. That's going to be our metal cation. That's nothing different now. We've always known that to be true. And then all these nonmetals here, again, it's kind of strange. I know it's a little unfamiliar to us, but that's actually all one ion. So I'm going to put a box around that. So that is going to end up being my anion, which serves as the polyatomic ion as well. Again, how do you know it's polyatomic? Because it is an ion. In fact, it's a negative one. But also, more importantly, it's got 2 carbons, 3 hydrogens, 2 oxygens all together. That's obviously polyatomic. It's multiple atoms to make the one ion there. Try the rest of them out. You have 4 other examples to help you identify polyatomic ions. Now, before I go on to actually break these down, one of the things that you notice is that it's kind of hard to identify them. So let's see what it might be useful here to see how to do so. You have been given this, and you probably don't know this that well, or if you haven't seen it yet, you should be able to find it on the files section of the PowerSchool page. But the polyatomic ions, there are several of them, and you're going to have to be able to identify all of them. So this is a list of common polyatomic ions. A couple things I want you to note about this breakdown. First of all, there are both names, formulas, and charges. When I say both, I mean there's actually names, formulas, and charges for a large majority of these. So if you look at these, right, for example, this section right here, these are all -1s. All of these charged are -2. All these have a charge of -3. And they're broken up that way to help you sort of organize how these are all put together. Secondly, they also have names and formulas along with the charge. So let's just arbitrarily pick this one right here, bromate, B-R-O-M-A-T-E. Bromate. Bromate, again, that's a polyatomic ion. How do you know that from just the name? Well, it's got an A-T-E ending. That's classic polyatomic ion. But more importantly, it has a combination of the element brom, right, core, and then the 8 together. So bromate altogether refers to the polyatomic ion. Now, what comes afterwards, this is where the challenge kind of starts to develop, is that you have Br, right, for bromine, that's no problem. The O referring to the oxygens, right, that makes it an 8, not just a bromide, but now it's a bromate. But then we also have a number of oxygens that go with it. That's very specific to the formula. So if you're ever referring to bromate, you have to know that it's referring to BrO3 with a -1 charge. So it's important to identify, again, all of it, all of it, again, including the names, formulas, and the charge that it goes with. A couple other things to note, too. I mentioned this earlier. Let's go ahead and look at nitrate and nitrite down here. So nitrate and nitrite. These two, again, are very similar because they both have the nitrogen core, right, the root element there, but they both also have a different ending, 8 versus ite, which sound very similar, but the distinction is important. Remember what we discussed before is that 8 has 1 more oxygen than ite, which would have 1 less compared to 8. So that's why we look at the formulas here, NO3 versus NO2, 8 and ite. So NO3 with a -1 charge, NO2 with a -1 charge. So these two, again, if you're not careful, you can be confused if you're not sure of the number, but also not sure of the ending. I also want to look at another grouping here and kind of keep that nitrate and nitrite in mind. Let's go and take a look at sulfate and sulfite. So these two are another polyatomic ions. I'm grouping these together, as you can tell. And sulfate and sulfite, sulf as a prefix refers to the element sulfur. And then you have the endings 8 and ite. So what exactly is different about these? Well, first of all, aside from the fact that this is part of the -2 grouping, right? So all these have -2 charges rather than -1. The endings, right, refer to a different number of electrons than what you saw here with nitrate and nitrite. So NO3 is NO3, is nitrate, whereas nitrite is NO2. But sulfate and sulfite, well, sulfate is SO4, not SO3, like we saw 8 here. So 8s don't always mean 3 or don't always mean 4. That's a very common mistake. So I'm going to bring that up to you now so you don't continue to mess that one up. And then if you have SO4 and SO3, all right, that's the relationship between sulfate and sulfite. So if you know sulfate is a SO4, you can very easily make the conclusion that sulfite will have the same charge but have one less oxygen. One more thing you want to overlook too, this is one more charge. This is the most common positive polyatomic ion that we'll see, and really the only one I'm going to ask y'all to know. And so that one's ammonium, which has an NH4+. So don't forget that's a polyatomic ion that you have to recognize as well. The rest of the sheet includes information, especially this section right here, that you'll want to know. The rest of it is just kind of some background information, which we'll address later. But definitely know that the metal oxidation states here, the group 1 metals, silver, these are all +1s, right? We already know this from before. Silver is a transition metal, and normally you would think transition metals are also multivalent, multiple charges are available. But we know that silver is an exception, so in fact it's always a +1. But then group 1 metals, right? We know that sodium, potassium, all those in the first period of the first group of the periodic table, right? All of these right here, these are always +1s. Same thing with +2 and +3 here. So go ahead and commit those to memory as well. Even those aren't technically polyatomic ions, it's included on the sheet just as a little reminder of where to look for this kind of information. So back to the slides, looking at the actual setup here. The name of the formula really hasn't changed much. There's one little bit that we do have to be careful of. So going from the name to the formula, again, the formula is the letters and the numbers. What exactly happens here? So again, no big deal about this first point. It's the same as before. The charges overall have to be 0. And the charges, again, are understood in the formula. They're never explicitly written out, right? So they're understood to be a part of that formula, but never shown. But this is where the new thing comes in, is that multiples of a polyatomic ion require parentheses and a subscript on the outside. So this is now again introducing parentheses, but for the formula. Let's go and see what magnesium chlorate does for us. So magnesium chlorate, again, it's important to identify what this is. Ionic compound, of course, because you have magnesium and metal, and then chlor, which is a non-metal prefix. So we know there's going to be some kind of a ionic compound, metals and non-metals. But now specifically, this one's referring to chlorate. So the way I'm going to start this off, I know that magnesium is a Mg symbol. Chlorate is ClO. Well, I'm not really sure, so again, I'm going to have to check my list of polyatomic ions. Chlorate right here, chlorate has a ClO3- charge, so I know ClO3 is the formula. And kind of going off of our sort of earlier work identifying the charges, magnesium is always a +2. That's a well-known established monovalent metal. ClO3 we just saw on the previous page there with the polyatomic ions, that's going to be -1. So how do I put this together, magnesium and chlorate? How do I put these together so it makes an overall neutral compound? Well, again, we're shooting for the least common multiple, which will be 2. So overall it wants to be +2. Overall this needs to be -2, right? +2, -2, those are going to make a neutral compound. So what does it take to make this happen? Well, magnesium, again, to go from +2 to +2, you don't need to have any extra magnesiums. 1 is fine. ClO3, that's a -1 charge to get it to -2. We have to double it. So to do so, what we're going to do is going to go ahead and put parentheses around this and put 2 right there. That's how we can show we can double it. So the final answer, again, is MgClO3 2. Why is it important to put parentheses around it? Well, it's because you have to make sure that you double the entirety of this. And you also don't want to lose meaning. So sometimes you might try to do something like this. Well, Cl2O6, right? So if you take that 2 and distribute it throughout, doesn't that mean the same thing? Not quite, because really the identity of the ion chlorate, excuse me, is ClO3. So you kind of lose that meaning going from here to doubling like that. So it becomes Cl2O6. That's not a recognized ion, so we don't write it like that. We definitely don't do it like that. So we lose meaning in the identity of what chlorite is. So I just do parentheses and then 2. Go and try the next two. Cobalt-2 nitrite. Again, this time it incorporates this Roman numeral here as a prefix, in parentheses. Don't forget what that means, right? That refers to something very specific. Going backwards from a formula to a name, this time you really don't have any new rules, except instead of using the ides all the time as an ending in your second element, right? It's not always just going to be chloride. Now you have the potential for ates and ites, and you have to know which one they are. But we talked about this earlier in identifying the polyatomic ions. For example, K2CO3. K2CO3. K is your potassium. That's a metal. That's going to be a positive charge. CO3, right, that collectively might be unfamiliar to you right now, but if you look at the list of polyatomic ions, go ahead and scooch down here, it's not anywhere there. CO3 is actually carbonate right there. So we know that the formula of CO3 refers to carbonate. So again, I can start this off by go ahead and jotting in that this is potassium. Right, for the K, and then CO3 together collectively is carbonate. So please don't try to break this down into carbon oxygenide or carbonide. That's not accurate. It has to be the entirety of the grouping together to know that it's carbonate. And then as a result, right, potassium carbonate, we have to know, again, based on our rules, do we have to include anything extra? Do we have to include any parentheses as a Roman numeral here? It turns out we don't, right? So please don't include anything there because potassium is monovalent. It's not multivalent, which would require a parentheses with a Roman numeral. Okay, so once more, go ahead and take a look at these two examples and give those a shot. And then finally, with mixed practice, there's a selection of 8 here. This one, again, is mixing all the different types of ionic compound nomenclatures that we have learned. So that includes your standard binary ionic compounds, but also now includes polyatomic ions. And don't forget that we have multivalent versus monovalent metals that you need to address as well. So when you go through these, I highly encourage you to take the time to say, okay, this is a ionic compound. It might be binary, it might have polyatomic ions, or it might have multivalent versus monovalent metals. So all these parts are important to identify as you go through these, which helps you be more accurate. And then, of course, this is a little extra practice to make sure you understand that there are certain errors that might pop up. So if you, again, are reviewing your own work and you see something like this happen, you know how to address it and why the correct way might not be represented on that piece of paper. All right, so go ahead and give these a shot, and that'll wrap it up.